I am with IIIT Hyderabad, and I'm going to talk about functional lower bounds for restricted arithmetic circuits of depth 4. So this work falls in the intersection of Boolean circuit complexity and arithmetic circuit complexity. So let's start with the famous question in Boolean complexity. So the P versus NP question. So it's been a long-standing open question to separate P from NP, and we have not been able to make much progress towards this. So let's look at the ecosystem around P versus NP. So we have a lot of classes which lie inside P, and there are a lot of classes which lie beyond beyond NP. So instead of looking at a separation between P and NP, we could ask for a coarser separation between, say, sharp P and AC0. AC0 is a set of functions that are computable by constant depth circuits with AND or NOT and MOD gates. And sharp P is a set of counting problems. So sharp P is a set of functions that count the accepting paths of a non-deterministic Turing machine. So now, instead of asking for a separation between P and NP, you could ask for a separation between, say, AC0 and sharp P. Or, on the other hand, you could ask for a separation between, say, NC and AC0, or P and AC0, or let's say sharp P and P. So there are a lot of problems that you could study in this Boolean function hierarchy. So let's look at concentrate on one particular class which we call AC0. So AC0 is a class of functions that can be computed by constant depth circuits with AND or NOT and MOD gates. So this is a class of functions. And what is known about AC0 is as follows. So back in '94, Eric Allender and Vivek Gore, they showed that permanent is a function which is in sharp P. They showed that permanent cannot be computed by polynomial sized uniform AC0 circuits. And in the non-uniform setting, Williams in a breakthrough result showed that there exists a function in exp such that it cannot be computed by polynomial sized non-uniform AC0 circuits. And with Murray, Williams further showed that there exists a function f in NQP such that it cannot be computed by polynomial sized non-uniform AC0 circuits. So NEXP is non-deterministic exponential time and NQP is non-deterministic quasi-polynomial time. So the work in this line of work looks towards finding a function f which is a class much smaller than NQP such that it cannot be computed by non-uniform AC0 circuits. So one possible question is there a function in sharp P or is there a function in NP that cannot be computed by polynomial sized non-uniform AC0 circuits? So at the end of the day, we would like to separate sharp P from AC0, we would like to separate NC from AC0 and so on. So one of the key ingredients in the proof of Williams is this characterization of AC0 by Beagle and Tarui, which by itself depends on the work of Yao. They said that every function in AC0 can be computed by a depth 2 deterministic circuit where the top gate is a symmetric gate, and into the symmetric gate quasi-polynomially many AND gates feed into, and into each of these AND gates polylog many variables feed. Right? So we have a deterministic circuit of depth 2. So there is a depth 2 is like the leaf to root path is of length 2. So every function in AC0 can also be computed using a deterministic depth 2 circuit where the top gate is some symmetric function, and into the symmetric function go the AND gates, and into each of these AND gates there are polylog many variables that feed into. Right? So what Forbes, Kumar and Saptarshi observed is that every symmetric function can be written as a univariate polynomial over the sum of its inputs when the field is large. So when the field is large enough, any symmetric function can be algebraized and expressed as a univariate polynomial over the sum of inputs of that symmetric function. So using this characterization, the depth to circuit which was given by Beagle-Tarui can be algebraized into the following algebraic expression. So any function f in AC0 can also be computed algebraically using the expression which can be written as sums of powers of polynomials. Here the number of summons is at most quasi-poly many, and each of these polynomials is they are such that their monomials are supported on at most polylog many variables, and this power is also bounded by quasi-poly. So every function f which is in AC0 can be expressed as a sum of powers of polynomials, and the number of summands can at most be quasi-poly. So we shall henceforth denote expressions of such form which are sums of powers of polynomials as sigma power sigma pi expressions. So this is sums of powers of polynomials. So now, to show that there is a function which is not in AC0, it is sufficient to show that that function does not have expressions of this form where S is bounded by quasi-poly. So I repeat, to show a lower bound for a function, say for a function against the class AC0, it is sufficient to show that that function does not exhibit expressions which can be written as sums of powers of polynomials of small size. Suppose there is a function f that needs expressions of this form where summands need to be at least super quasi-poly, then that function cannot be in AC0. So now, a strategy towards proving AC0 lower bounds is to show that there exists a function f such that the evaluation table of f over 0 1 power n is not equal to the evaluation table of any small sigma power sigma pi expression. This small is bounded by quasi-poly. This small we shall instantiate with quasi-poly. So, a strategy to show AC0 lower bounds is to show that there exists a function f such that its evaluation table is not equal to the evaluation table of any polynomials that can be expressed as sigma power sigma pi. Right? So small sigma power sigma pi expressions. And we further want to show that this particular function f lies in a class that is not much larger than AC0. So we would like to show that this function f lies in a class which is say smaller than sharp p, smaller or equal to sharp p. Okay. So we are good as long as this function f lies in a class that is smaller than nqp from the current state of affairs. So towards this, what we do in this paper is to show that there exists a function f which is computable in gap L, which is a very small class. It's a class which is in P, and it is such that the evaluation table of this function f is not equal to the evaluation table of any small and bounded individual degree sigma power sigma pi expression. So we find a function f such that the function is in gap L, and we show that the evaluation table of f is not equal to the evaluation tables of any of the polynomials of bounded individual degree that can be computed by small sigma power sigma pi expressions. So here we have a caveat. We don't show it for all small sigma power sigma pi expressions. We show it for all sigma power sigma pi expressions that output polynomials of bounded individual degree. So we say a polynomial p has bounded individual degree r if the degree of the polynomial with respect to each of its variables is at most r. Right? A multilinear polynomial, for example, has bounded individual degree 1. I repeat, we show that there exists a function f which is computable in gap L such that its evaluation table is not equal to the evaluation tables of polynomials that are output by sigma power sigma pi expressions of small size. So we show this result by proving functional size lower bounds against restricted arithmetic circuits of depth 4. So now let me tell you what these restricted arithmetic circuits of depth 4 are. So arithmetic circuits are directed acyclic graphs whose leaf nodes are either constants or variables. Their non-leaf nodes are either addition or multiplication, and edges could be labeled by constants. And now every node computes a polynomial. So here the leaf node computes, this leaf node computes a polynomial x1, and this leaf node computes a constant polynomial 1, and these two feed into this addition gate, and this node computes a polynomial which is 1 plus x1, and this 1 plus x1 feeds twice into this multiplication gate and powers it to 1 plus x1 square. Right? So now this directed acyclic graph generates a polynomial from constants and variables by applying algebraic operations on them. So the complexity of computing a polynomial is the number of nodes or the number of algebraic operations in this directed acyclic graph. So the circuit size is the number of nodes present in this directed acyclic graph, and that is a measure of complexity of a polynomial. And we also have a notion of circuit depth, which is the length of the longest leaf to root path. So in both of these examples, the longest leaf, so this is a root and this is a root in this example, and the longest leaf to root path is 2 in both of these. So now the sigma power sigma pi expressions that we have spoken about are restricted depth for circuits of the following form. So you can see that the powering gate is actually a multiplication node where all its inputs are the same. So for example, this multiplication gate is a powering node. Right? So that is why it's a depth 4 circuit. So leaf to the product gate to the sum gate to the powering gate to the sum gate. So it is depth 4. And it's restricted because the top product gate is restricted to have all the inputs to be the same. So now we want to show functional lower bounds against restricted depth 4 circuits of this form. So what are functional lower bounds? So let's say we want to prove a functional lower bound of S for a polynomial P against a circuit class C. We say a polynomial P has a functional lower bound of S with respect to a class of circuits C if the evaluation table over 0 1 power n of any circuit in C of size at most S is not equal to the evaluation table of P over 0 1 power n. Right? So in this context, we have this C to be instantiated with sigma power sigma pi circuits and S to be instantiated with quasi-poly. So those are the kind of lower bounds that we are looking at. So let's look at bird's eye view of proof, how we go about proving such results. So we first show that there exists an explicit polynomial P such that it is not functionally equivalent to polynomials of bounded individual degree that are computed by small sigma power sigma pi circuits. So ideally, to show lower bounds against AC0, we'd like to show that there exists an explicit polynomial such that it is not functionally equivalent to polynomials that are computed by quasi-polynomial size sigma power sigma pi circuits. However, we are able to show this result with a caveat of bounded individual degree. So what we are showing here is that there exists an explicit polynomial p such that it is not functionally equivalent to polynomials of bounded individual degree that are computed by small sigma power sigma pi expression. That is, polynomials of bounded individual degree that can be expressed as small sigma power sigma pi expressions. So that's the result. That's the step 1. And then we show that this particular function f is in gap L. So there exists a function f in gap L such that it simulates the evaluation of the polynomial p, so the same explicit polynomial p over 0 1 power n. That is, we show that there exists a function f, an explicit function f, which is in gap L, that simulates the evaluation of this polynomial p over 0 1 power n. So this follows from a result of phi, and we'll tell you how this is proved. So the polynomial of interest is the iterated matrix multiplication polynomial. So iterated matrix multiplication polynomial is given by the source to sink layered graph. So the polynomial is given by the sums of weight of all source to sink paths. So here you take this layered graph such that each of these layers has n root nodes and there are d many layers, and every edge in this source to sink graph is labeled by a distinct variable. That is, all edges are labeled by variables and all these edge labels are distinct. So now the polynomial of interest I that we denote by IMM n comma d. So this family is parameterized by n and d, where n denotes to the number of nodes in each of these layers and d denotes the number of layers. Right? So this polynomial, if you expand it, it is a very nice structure, and alternatively this can be thought of as the 1 comma 1 entry in the product of the matrices x1 to xd, where each of these matrices is defined on a disjoint and distinct set of variables. Right? And it is well known that this family of polynomials can be computed efficiently. That is, they have polynomial sized arithmetic circuits. Further, they have depth 4 circuits of size n to the root d. And if you consider your field size to be large, you have sigma power sigma pi expressions of size n to the root d. So that is the polynomial of interest. And we want to show a lower bound for this polynomial against the sigma power sigma pi expressions. So the broad theme of such proofs is as follows. So we usually define a suitable complexity measure. So this complexity measure, say gamma, takes as input a polynomial and outputs a real value. And we need the complexity measure to have the following properties. So for any polynomial f that is computed by small sigma power sigma pi circuits in this setting, we want the measure to be small. So this small and this small are different. And for the target polynomial p of interest, that is IMM, we want the measure to be large. I repeat. So we want to define a complexity measure that distinguishes between the polynomial of interest and all the possible polynomials that are computed by the circuits of small size. So here we are interested in distinguishing IMM and polynomials of bounded individual degree R that are computed by quasi-polynomially large sigma power sigma pi circuits. And towards that, we define a measure that we call multilinear shifted evaluation dimension. So this measure is based on the measure of shifted evaluation dimension that was shown by Forbes, Kumar and Saptarishi. And it is important to note that if P and Q are two different polynomials that are functionally equivalent over 0 1 power n, then this measure is identical for both of these polynomials. So most of the analysis of this paper goes into establishing the following. And step two, so this can be summarized using the following theorem. So for certain range of d, k and r, we show the following theorem. So this is for a large integer n, and the range of d, k and r, which are shown as follows. We show that if there is a polynomial p of bounded individual degree r that computes that is functionally equivalent to IMM n comma d on 0 and power n square d, then this sigma power sigma pi expression must have size at least n power omega k. I repeat, if there is a sigma power sigma pi expression that outputs a polynomial of bounded individual degree at most r, and if that polynomial is functionally equivalent to IMM n comma d over 0 1 power n square d, then this particular expression must have size at least n to the omega k. And for this range of parameters, it is easy to say that this value can at least be quasi-poly. This can be super quasi-poly. And the step 2, so it was shown by Vinay, Toda and Dan in 1991 that evaluation of iterated matrix multiplication over 0 1 power n square can be simulated in Gabel. So this is a well-known result. So both of these steps give us the theorem that we need. So let's look at this theorem again, that we have the main theorem that we have spoken about. So for large integers n and parameters d, k and r such that d lies between log square and sublinear, and r is at most d by k square, we show that any polynomial of bounded individual degree r that is functionally equivalent to IMM over 0 1 power n square d, if it is computed by a sigma power sigma pi expression, then that expression must be of large size. So if we can improve this particular theorem, for a wider range of r, or make it independent of r, we can actually prove the separation of AC0 from Gabel. Or show this theorem for a wider range of r for some other polynomial, maybe in a larger class, say sharp p, then that could lead separation of AC0 from sharp p. So that's our result. And along with this result, so this was the result that we spoken about. Along with that, we also prove low bounds for depth 4 circuits of bounded formal degree. So this is in comparison to the work of Forbes, Kumar and Saptarshi. They show low bounds for depth 4 circuits of bounded formal degree for polynomials in V and P. So we show low bounds for a polynomial in VP, and we get that our result holds for a wider range of individual degree. And that's about it. So we'd like to improve the dependence on R in each of these results. Thank you.